All right, it's 2 o'clock, so let's get started. There's a chair back there. So just a few quick announcements. Quiz 2 is out on Blackboard. It's due on Saturday, just like Quiz 1 was. Homework 1 is out, so although it's not counted for any credit, I highly recommend that you do them because it's really good practice. And the solutions for last week's quiz and the recitation, like the examples that we did in recitation last week, are also posted on the website. So are there any questions before we get started? This is the perfect time to be asking questions if you're confused about anything with the material. Otherwise, I'm just going to go into examples. Yeah.
So quiz 1 went over a lot of sort of minor points of how DFAs and things work that weren't really covered in the lecture. So we were, and there wasn't also a very clear explanation for that in the book. So how would we go about it? I don't know if that's the way the rest of the quiz is formatted, but how would you suggest we go about preparing for the quiz?
So preparing for the quizzes. Start them early, and then at least try to understand the question. You're absolutely free to ask anyone you want about what the question means, because if you don't understand the question, then there's no way you can get the answer anyway. So feel free to ask those questions. Feel free to ask your classmates questions about how to understand the question. And the whole point of the questions, I designed them as for you to understand the material at a deeper level than you would get through lecture. So the one about, say, the alphabet being the empty set instead of just being at least one inside. That's a question that came about last semester, and I thought was actually pretty interesting because it forces you to think about the material better. And I can actually cover that at the end, but it actually shows one thing that's pretty interesting. So so everyone knows what the star operation is, right? Right? So let's consider the sigma star. What does that mean to you? Well, it means all the strings that you can write over sigma. So what if sigma is the empty set? Well, by definition, that's just the empty set star, right? Well, let's figure out what this is. Empty set star is the union over all k at least 0 of empty set to the k. So picking things from the empty set k times for any number of k's. What if k is 0? What is it?
Empty set.
And k is 0. Well, picking 0 things from the empty set is the empty string, right? So that's because we saw that the empty string is in every star of any language. Well, what if I chose 1 time? Well, it's just the empty set itself because I'm picking 1 time from the empty set. So that's just the empty set itself. Union, well, twice from the empty set, and then so on. What are all these? Well, empty union empty better be still empty. So the set containing the empty string union empty set, I think is still the empty string. So that shows that the empty set star is the set containing the empty string. How would you prove this using DFAs? Well, consider having a DFA with alphabet, which is the empty set. Well, we have to have a start state no matter what, because the 4th part of the DFA says there must be a start state. Can there be any transition if the alphabet is empty? No. So there may be other states, but I can't get anywhere with this. Is this the only possible DFA like this?
Infinitely many.
Oh, I can also make another one where the start state is the final state. What language is the first one? Does the first one accept anything? No, it accepts nothing. So its language is empty set. This guy's empty set. What is this one? Does it accept every string?
Yes.
Yeah, because there are no transitions to do, so it accepts every string. So this is sigma star. But what is the string that it accepts? The empty string. So empty set star is the string, just the set containing the empty string. So back to the question. It forces you to think about not only DFAs in a deeper way, but it also makes you think what kinds of DFAs are possible using this. So it's just thinking about things in a more deep way. Does that answer your question? Are there any other questions before we start? So the handout has 4 questions on the front and 3 on the back. There's absolutely no way I'm going to get through the last 3, but so those are purely for your practice and better understanding. We'll try to get through the first 3, and I'm pretty sure we won't get to number 4 today. So when we were talking about material last week, what was the major thing that we were talking about? The DFAs, right? But what was the thing that we were able to prove about, say, putting DFAs together? Right, so I want to put DFAs together to make larger DFAs somehow. So what kind of operations were we thinking about in terms of DFAs? Concatenation. We were thinking about concatenation, but what were the other 3 we were talking about? Union, intersection, and which one? Complement. And we were talking about these because we noticed that languages of DFAs are just sets of strings, but they're sets. And when you notice, when you have 2 sets, the first thing you want to do is put them together using union, intersection, and with one of them doing complement, getting every string that's not in the particular set you have. So what were we able to show with these 3? That if I have a DFA for one, then what can happen? So let's say complement. If I have a DFA, what can I say? It's closed under complement. What does that mean? That means that if I get a DFA for the complement of whatever language the original had, I still have a regular language, right? And so how did we actually do that? How did we get a DFA for the complement of the language? Yeah, we flipped the final and non-final states. So if it was non-final over here, I'm going to make it final over here, non-final over here. We just swapped the states. And we noticed that that was true because every string has only exactly one computation. And so the homework actually has a question about how this won't work for NFAs. But for DFAs, it works quite well. So how did we actually do union and intersection? So if I have 2 DFAs, I want a DFA for the union or intersection of their languages. So this is a little bit more complicated. So let's talk about 2 given DFAs. So let's just say I have M1, which has this definition with 1s in the subscript, and M2 with 2s in the subscript. All right? So let's suppose that we're doing union here. So what was the main idea we thought of to make a DFA for the union of these 2 guys? So an idea that doesn't work is whatever string we have, feed it to both machines and see if at least one accepts. And then we accept if that's the case. So why would that idea not work? Just feed the input to both machines.
Need the same input twice.
Yeah, the same input twice. If I consume a character of the input, is it gone? Yeah, it's gone forever. I can't go back to, like, say, reverse the tape or whatever. So I only have one chance to read the input here. And so what was the main idea we thought of to read the input at the exact same time for both machines? Run the machines in quote-unquote parallel. And how did we actually achieve that parallelism? Well, what we can do is we can keep track of what state we would have been, say, in M1, and what state we would have been in M2 if we somehow ran the machines one at a time. Yeah.
That would be the product construction. Right?
Product construction, good. So that's exactly what we're gonna do here. So I wanna make a machine M, which is the union of these two languages. And the suggestion was the product construction. So I gotta figure out each of the 5 pieces, obviously. But what is the set of states gonna be? Well, I gotta keep track of what state I was in the first machine and what state I was in the second machine. Do I need to do that for all possible pairs? I better, because I may need every single one of those. So how do I do that? I just write Q1 times Q2. Just the Cartesian product of 2 sets. So what are the elements in this column?
Ordered pairs.
Ordered pairs, right? So I'm keeping track of all possible ordered pairs between Q1 and Q2. All right? I think the alphabet's not going to change. I'm going to have some new transition function, but it's not quite so simple to write here, so I'm going to write it below. So now I got to figure out what the start state and what the final states are. I'm going to ask this question several times as we're doing this. What are the states in this machine represented? It was the same suggestion as earlier. Your suggestion again?
Ordered pairs.
Ordered pairs, right? This is just the set of all ordered pairs. So every single state in here is going to be an ordered pair. So what do you think the start state is? An ordered pair, okay? So what do you think is going to go in this ordered pair?
Q01, Q02.
Right. I got to figure out what the start state is of the first machine and start state of the second machine. Well, they're written right here, so I can just write them right here. Q01, Q02. And the set of final states is not quite so easy to write here, so I'm going to write it down below. Are we good so far? Okay. So now let's figure out what the transition function is. For any DFA, what does the transition function take as input?
Previous state.
A state and
An input.
not a string. Some character from the alphabet, right? I'm reading one character at a time, so it's some character from the alphabet. Again, what are the states of this machine? Ordered pairs, right? So in the first part of the transition function, I better write an ordered pair. So I'm going to write Q1, Q2. And let's just say we're reading character A for convenience. What does the transition function output?
An ordered pair.
An ordered pair. Because, well, it outputs a state, but in this case, it happens to be an ordered pair. So, what's going to go in this ordered pair? Remember, what does the first coordinate of the ordered pair tell me? Right, it tells me, and if I were to run M1 right by itself, this is the state I would have been in. But I'm keeping track of 2 things. So how do I figure out what the first guy is going to be here?
Use that machine's transition
The
function.
transition function of the first machine, right? So that's going to tell me where it's going to go. Oh wait, what state am I in of the first machine currently? Before I read this A. I'm in Q1 right now, right? Before I read the A, I'm in Q1. So now I got to figure out what's going to go here. Well, I look up in the transition function, delta 1, with the current state that I'm in, which happens to be Q1 right now. Q1, reading an A. All right? So, yeah, so now I'm just going to keep, as I'm reading the string, I'm just going to keep looking up in the original transition functions what to do for each of the 2 parts. So what do you think is going to go in the second one? The second transition function. Good. Second transition function with Q2 instead. Because that's the state I was currently in. Are we good? Am I done?
No.
No, what have I forgotten?
Final states.
Final states. All right. So let's figure out what the final states are. Well, I think the final states are a set, right? So final states are a set, so I'm going to write down a set. What are the states of this machine? Ordered pairs. So I better write down a set of ordered pairs here. So I'm going to write down again Q1, Q2. And so now I got to think, what has to be true of Q1 or Q2 in order for me to say whether the state in this new machine is actually a final state? Question for you. Was the first 4 parts that we did here have anything to do with intersection or union? No, so the only difference is in the final states, whether I'm doing union or intersection, which is kind of nice. So let's say we're doing union here. So what has to be true of Q1 or Q2? Well, let's think. If Q1 is final, do I care what Q2 is? No, because if we ended up in Q1 of the first machine, we're already in the union of their languages. Okay, so if Q1's an F1, I definitely want this pair to be a final state. If Q2 is final, do I care what Q1 is? No, because again, I would begin the union if M2 was a final state at that point. So I write or Q2 is an F2, and obviously if both are true, then I'm definitely in the union for sure. Is that good for everyone? Question for you. Suppose I actually meant to tell you intersection instead of union, like I just completely screwed up. Do I need to do this whole thing again? Oh, so what would I have to change in order to say I'm doing intersection instead? Oh, I only need to change one word from making it union to intersection. Questions so far? All right, so let's actually do some of the exercises on the handout. So the first one is, I want all strings in 0, 1 star such that the number of zeros in W is not 2. So any string that has 0 occurrences of 0, 1 occurrence, 3 occurrences, or 4 than that. I just don't want 2. I hate the number 2 for some reason. All right, so let's try to figure out, maybe we can use these operations to our advantage because they're designed to allow simpler languages so that we can make DFAs for those, and then since they're closed under these operations, then we can make the more complex guys. So how do you think maybe we could make this somewhat simpler than what it is right now? So it's not 2 is the condition that I want. Is there a simpler condition that's related to that? Exactly. So the thing that jumps out to me is that not equal thing. It seems like, this is not true, but it seems like at a first glance, this is somewhat difficult. I need to check that the number of zeros is equal to 0 or 1 or 3 or 4 or 5, and there are infinitely many possibilities. So that seems kind of difficult. What the suggestion was maybe we can look at the complement of this language where it's equal to 2, make a DFA for that guy, and then show under closure of the complementation that we can get a DFA for the original one. So if I call this guy L, I want to look at L bar, which is the same thing, same definition of W, such that the number of zeros in W is exactly 2. Okay? So how would I even approach doing that? Well, let's see. Suppose I had an input string where there were 3 zeros in it. Or I have read 3 zeros of this input and there probably is some other zeros in it. Will I ever accept after that point? If I've read 3 zeros, will I ever get to 2? No. So I need to only keep track of whether it's exactly equal to 0, exactly 1, exactly 2, or 3 or more. Okay? So each one of those is going to be a state. So I'm going to make 4 states now. Q0, Q1, Q2, Q3. So this, in my mind, is going to represent seeing 0 zeros so far, 1 0 so far, 2 zeros so far, and then 3 or more zeros. So what's the start state?
Q0.
Q0, because I've seen 0 zeros at that point. What is Q0 going to do on 1? It's going to loop. Why? Because if I ever see a 1, does that change the number of zeros that I've seen? Certainly not. So that's going to self-loop on 1. What about the other states then on input 1? They're also going to loop because, again, they're not going to change the number of number of zeros that I've seen. So 1, 1, 1. That was easy. Am I done?
Final states.
Well, final states, but what else have I forgotten?
The zero.
The zero transition. This is a pretty boring DFA as it is anyway. So what is Q0 going to do on input 0? In my mind, it should say, okay, now I've seen exactly 1 0. Oh, that's what Q1 represents. So it's going to come over to Q1. What do you think Q1 then is going to do on input 0?
Q2.
Go to Q2. Good. Q2 on input 0? Go to Q3, yeah. Oh, wait. Where's Q3 going to go? Oh, yeah. We wanted to represent 3 as at least 3. So if I see another 0, I'm just going to stay there. Good. All right, so now I got to figure out the final states. So I know from closure into complement that all I'm going to do to get back to the original is just flip the states from being final to non-final. So for L bar, what would the final states be here?
Q2.
The Q2 by itself, because that's the only condition that I want to accept for. So what would the final states be for the original language L?
Q0, Q1,
Q0, Q1, Q3. All right. So because I'm just flipping the states of whether they're being final or not final. Okay? So the idea was to make the language simpler in order to make a DFA for that, then just use these operations to get to the thing that we want. Okay? Any questions so far? Okay. So now let's do the second one. So it says that we want an even number of zeros or exactly 1 occurrence of 1 or 2 occurrences of 1. Okay? So does there anything stand out to you as being somewhat important in this? Is there any word that's important?
Even.
Oh, the and one, right? Because it's saying that I only want this string in the language if this condition is true and this condition is true. Oh, does that sound like some operation that we just talked about? Oh, intersection, right? Because I want it in this guy's language and this guy's language. So if suppose I can make a DFA for this and a DFA for this. Can I make a DFA for the whole thing? Yeah. So let's make a DFA for both of them. So let's say L1 is the first one. So I want to check if the number of zeros is even. Do I have a way of doing that? Yeah, so how would I go about doing that?
You sneak 2 states and you move between them.
Ah, yeah. I'm going to make 2 states to represent how many zeros that I've seen, either if it's even or if I've seen an odd number so far. So I'm going to make 2 states. I'm going to call them Q even and Q odd. Okay? What would the start state be?
Even.
I think it's going to be Q even because I've seen 0 characters and 0 is even. So where does Q even then go on 0? It should go to odd because if I've seen an even number of zeros and then I see one more, now I've seen an odd number. Where's Q even going to go on input 1? Itself. Why? Because it's not going to change the number of zeros that we've seen. Good. I'll do it up here. What about odd? Where's it going to go on 0? Q even for the same reason. We've seen an odd number. See one more, seen an even number. Odd on 1. It's going to again stay for the same reason. Okay. Am I done with that DFA? Oh, what have I forgotten? Oh, final states. What is the language of this DFA as is?
0, 1.
Does this DFA ever accept anything? No, there's no accept states. So what is its language?
The empty set.
Empty set. Good. What is the set of final states then that I want? I want Q even to be the final state because I want to check if the number of zeros is even. Good. So that's my accept state. Okay. So now I want to make a DFA for the second one, which is the number of ones in the string is 1 or 2. Any strategy for that one?
It's going to be the same as the first one.
Oh, yeah. It's almost exactly the same as this one we did before. Well, the complemented version, but it's almost exactly the same. Oh, wait. I'm checking number of zeros there, and I'm checking number of ones here. It's not going to work here. Or is it? Is it going to work here?
Flip the 0 and 1.
Oh, yeah, I can interchange the role of 0 and 1. So that's exactly what we're going to do. So Q0, Q1, Q2, Q3. Start state again. So where are the 1 transitions going to go? Are they going to be the self-loop ones or the ones that go across?
Across.
They're going to go across because up here they are doing the role of 0 because I want to check the number of ones here. So 1 here, 1 here, 1 here, and this one's also going to self-loop on 1. All right. So what are the 0 transitions going to do? They're going to self-loop because they're taking the role of the ones up here. Good. So 0. 0, 0, 0. Okay? So what are the final states going to be of this DFA? What do you think?
Q1 and Q2.
Q1, Q2, yeah. Because those is mirroring what we did up there. So those are my final states. Am I done with this problem? Oh, wait, what have I forgotten? Oh, shoot, the whole product construction thing. Doing all this stuff. So let's figure out how we're going to actually accomplish this. How many states is the product DFA going to have? 8. And how do you know that? It's because I want to keep an ordered pair with even as the first guy, and all of these as the second, odd as the first guy, and all of these as the second. So it represents I'm in Q even on the first machine, and one of the sticks in the second machine, or Q odd of the first machine, one of the others in the second. So we got to make 8 states. So the way I usually write these to make it easier for me is I'm going to write it with 2 subscripts. The first one coming from the first machine, and the second coming from the second machine. So I'm going to call these Q even 0, even 1, even 2, even 3, and then odd. So I'm going to make states like Q even 2, Q even 3, Q odd 0, Q odd 1, Q odd 2, Q odd 3. Okay, it's just all of the ordered pairs of the two machines, states. Good with that? So now I gotta figure out the other 4 pieces. Well, I know the alphabet, so that's easy. What's the start state of this machine? Or should be the start state?
Q even 0.
Q even 0, that should be my start state. Just remember that the names of states can be anything arbitrary. It doesn't have to be corresponding to the original machines, but it's just helpful for me. I could have made any one of these states, but this one seems the most intuitive to me, because they were the start states of the original machine. Okay? So I'm going to do final states at the end. So let's figure out the transition function. So where do you think Q even 0 is going to go on input 0?
Q 0 on.
Well, yeah, so let's think about it. So I'm currently here of the first machine and here of the second. So I got to figure out in both machines, where did I go on input 0? Or where would I go? Where would Q even go on input 0? It's going to go over to Q odd. So in my brain, I'm going to write down Q odd. Right? So that's a staple. Q 0 on 0, where does that go? Well, it does that self loop. So again, in my brain, I'm going to write down 0. So the whole thing I wrote down is odd and 0. Oh, and I have that state right there. So even 0 is going to come down to odd 0 on input 0. Where does even 0 go on 1? So I'm here again. Where does even go on 1? Back to itself, good. So I write down even. Where does Q0 go on input 1? It goes to Q1. So even 1. 1 is not even anyway, but it goes to that state. Okay? Let's do odd 0. So I'm in odd 0. Where am I going to go on 0? So where does odd go on 0?
Q.
It's going to go to Q even, so I write down even. 0 on 0, where does it go?
Itself. 0.
Back to itself. So even 0. Oh, that's that state right here. Odd 0 on 1. Where does odd go on 1? Back to itself, yeah? Q0 on 1, where does it go? Don't leave me hanging.
Q1.
Q1, yeah. So odd 1. Oh, I have that state right here. And you're doing this at this point, and you say, is there kind of some pattern that we can see here? So is there a pattern that we can see? Yeah. Can anyone see a pattern? Yeah. Well, what is it then? Oh, okay. So let's take each one of them one by one. So let's consider the 0 transitions first. If I'm in this machine, no matter what state I'm in, I'm going to go to the other state. What does that mean over here? That means I'm going to switch rows. No matter what state I'm in, I'm going to switch to another row. But what column am I going to be in? Well, what are all the states doing on input 0 in this machine? They're staying in the same state. Oh, well, those correspond to the columns. So different, the other row, same column. So what do you think even 1's going to do on input 0?
Odd 1.
Odd 1, purely from that reasoning. Different row, same column. Odd 1 on 0? Even 1, good. What do you think the 2 states are doing? On input 0, sorry.
Same thing.
They're going to go between each other, yeah, on input 0. Good. What about the 3 states? Well, 2 states, but they're named 3. I think they're going to go between each other again for the same reason. Now, not all DFAs are going to have a pattern like this, but we can see a pattern forming here. All right, so what about the 1 transitions then? Maybe they have a pattern too. Do they have a pattern? Well, let's see. So what do the 1 transitions do in this machine? They do self loops. So that must mean that we're going to stay in the same row no matter what state we're in. So no matter what state we're in the same row. Here, what are the 1 transitions doing? They're progressing until I get to 3 where I do a self loop. So what do you think even 1 and odd 1 are going to do on input 1? Well, they're going to progress to 2, but are they going to switch rows? No, they're not going to switch rows. So I think even 1 is going to go to even 2, and odd 1 is going to go to odd 2. Okay? What are the 2 states going to do in input 1? They're going to go to 3, I think, right? If I make a mistake, please tell me. Wait, if they're going to keep progressing, shouldn't there be a 4 that I go to with the 3 states?
No.
Oh, they're self loops. And let's figure out why. Because I'm going to stay in the same row no matter what. But in this second DFA, I'm going to loop on input 1. So it's a self loop in both cases. Am I done making this DFA? I may be done with the transition function, but what have I forgotten?
Final state.
Final states, okay. So remember, none of what I did had anything to do with intersection. But now I gotta figure out what is the intersection. So how do I figure out what the final states are going to be for intersection? Well, I gotta think, what are the final states up here? And the second coordinate has to be one of the final states in here. So it has to be even and 1 or even and 2. Those are my only possibilities of both coordinates being a final state. So those 2 are my final states. Okay? Yeah.
If it was, instead of intersection, if it was union, would the final states be different?
Very good question. So let's do that. If I instead said, oh no, I don't want and, I want or, how would I go about doing that? Fixing that?
You would add Q odd 1 and Q odd 2.
Oh, okay. So I gotta think, well, if Q even is the first coordinate, is that state gonna be final? Yeah, it's the union. So every even state is gonna be final. That's final, now this is final. And any state that has 1 is a final. And any state that has 2 is also final. So this one is already final. And I'm gonna add this one. This state's final, this one's not final, so I'm gonna add it. Okay? Does that answer your question? So I'm gonna do a related question because we don't have enough time to probably do the next one, but so the 4th question asks, is something or something else, but not both. Yeah.
You count 0 as multiple.
Yes. Yeah. 0 divides 3 evenly. Well, it's 0, but yeah, it divides it evenly. It's multiple of 3. So what if instead I said, I made this longer, but I said, but not both. So I don't want both conditions to happen at the same time. Do I need to do this whole thing again? No, so wait, what do I need to change? Oh, okay, it's the set of final states again. So how do I figure out what states to remove from the set of final states here? The ones where it's both, right? Those are the, right, because that's what but not both means. So how do I figure out what ones have both being final? Is that just the intersection? Ah, so the but not both thing is just union minus the intersection final states. So what were the intersection final states here?
Q even 1, Q even 2.
Q even 1 and Q even 2. So it's really nice that all of these operations are related to each other. Any questions on this?
What did you just say, but not both is? It's the intersection.
It's the final states corresponding to the union. Take out the ones that correspond to intersection from being final.
Okay.
Not literally delete, but take them out from the set of final states. Any other questions about that? So I don't have enough time to finish the next one, but let's actually start it. So when you notice this here, what is the most important word of the third question? Or, yeah. So what operation does that correspond to? Union, yeah. I want one of the two conditions to be true, at least. Well, can I make a DFA for the first part?
You have it? Oh, yeah.
Yeah, we already made that DFA. So I might as well just write it down again. You even right? I'm just going to write that down again. Can I make a DFA for the second part? Number of ones is not a multiple of 3. So when you think multiple of 3, what's your general strategy for doing that? Remainders, right? So how many possible remainders are there with 3? 3. Yeah, and they are 0, 1, and 2. What about 3? No, because then I would be able to divide it evenly. So I'm just going to make 3 states: Q0, Q1, Q2. What's the start state? It's going to be Q0 because if I've read 0 characters, well, I've read 0 ones, so therefore it's a multiple of 3. And it divides the remainder 0. So now I got to figure out where they go on 0 and 1. So where does Q0 go on 0? Itself. Why? Because it doesn't change the number of ones. So this does a self loop on 0. What about Q1 and Q2 on 0? Same thing, because it doesn't change the number of ones. So that simple fact that it doesn't change the number of ones we've used a couple times now. But now we got to figure out what happens on 1. So where does Q0 go on 1? Q0 on 1. Q1. Goes to Q1. Why? Because if I've seen a multiple of 3 number of zeros and I see one number of ones, then I see one more 1, then I've seen a number which, if you divide by 3, the remainder is 1 because I added 1. So it goes to Q1 on 1. What about Q1 on 1? I think it should go to Q2 because if I have a remainder of 1 and I add 1, I think that's 2. But wait, shouldn't Q2 go to some Q3? Oh, it goes back to Q0 because if I've seen a multiple of 3 and I add 3, I still have a multiple of 3. So Q2 should come back to Q0. Okay? And I want the case where it's not a multiple of 3. So what are the set of final states going to be? Q1 and Q2, because Q0 is the multiple of 3 state. So I want those two. Anyone want this 8-state DFA still there? So I'm going to erase it. Not enough room. All right, so am I done with this? Well, I literally erased to make more room, so I definitely am not done. So what did I forget? Doing the product construction. Okay. So how many states are going to be in the product construction? 6, because it's 2 times 3. So let's do the same convention as we had before. except I'm going to do it long ways this time. So odd is going to have a column instead of a row. Q even 1, Q even, oh no, odd. I confuse myself sometimes. Q even 2, Q odd 2. All right. So we might not get to everything, but what's the start state going to be of this machine? Q even 0, because those are the two start states of the machines. What is Q even 0 going to do on 0? Go to Q odd 0 for the same reasons as the one we had before. It's going to switch between odd and even, and the states in the second DFA all loop on 0. Oh, wait, so what does that tell you about what the 0 transitions are going to do? It's always going to switch between odd and even, but is it going to ever change the row that it's in? No, because it always self-loops in the second DFA. So, like the other example, we can have behavior that's very, very similar. Okay? Now I got to figure out where the 1 transitions go. So where do you think the 1 transitions go?
Down.
Oh, they go down, 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 right? So Q even and Q odd both loop on 1, right? And the Q0 always goes to Q1 on input 1. So where do you think these two states in the 0 row are going to go on input 1?
The state one. Just down.
They're going to go down, right? Because they're going to stay in the same column because they stay in the same state over here, but they're going to increase 1 over here. Where do you think the 1 states are going to go? Go down to 2, good. And where do you think the 2 states are going to go?
0.
They're going to come back because they came back in the second DFA. Good. Am I done?
Final state.
I sure can't tell when I'm done, right? So, how do I actually find out what the final states are here? Well, what operation are we doing? Union, right? So, how do I find out what the final states are? Any state that has even in it, make it final. Because if that's satisfied, then we're already in the union. So those 3 are final. Any state that has 1 in it, make it final. That guy's final. This one's not yet. Any state that has 2, make it final. Oh, make this one final. Questions about anything related to this? All right, I'll see you next week.